So the book is called Bioprocess Engineering, and the author is Pauline. That is Pauline Duran. This is, I should say, the main book. And secondary books that I will use, and when I do, I will point out, will be um, um, the book by, I'm trying to remember, I think it's Bioreaction Engineering. Bioreaction Engineering. And there are three authors, but the first author is John Willardson. And the other book, well, I think only at the end, this will be used very little. This is Energetics and Kinetics in Biotechnology. And this is by a guy called Ruels. This is not, so this book is not, the, the book by Ruels, I should mention, is not easily available. But so the material covered from here will be made available to you. But the first two books are easily available, and you can easily, well, I don't think I should be saying this, but you can easily download it from your favorite website for pirated books. Okay, so I should now um, tell you a little bit about what the course is about. Um, um, the course is about, so these are course contents. So just put it in kind of perspective. Um, this is basically how you, these are the principles that govern, these are, let's say, principles that govern uh, actually reaction kinetics. Reaction kinetics. This you have already done, I suppose, in uh, chemical engineering. Uh, when they interact and and their interaction with uh, from, I'll explain this word in a minute, advective or transport processes. So basically, we want to know. First, we'll start off by understanding just the speeds with which the reactions take place. Once we have an understanding of how these reactions take place, then you add onto it other things that take place. And you have already done this, but this is being done in the setting of biological reactions, which are very different. And so I'll point out that difference in a minute, but I just want to point out that here is a simple example, two simple examples. Here is a reactor. If it is well stirred, then I can do a reaction inside. I can do a reaction in this reactor. And if it is well mixed, then I have a pure kinetic problem. But the moment I add a feed going in or something going out, right, then I have added transport components, which then change this from a pure reaction problem to a reaction problem plus some, what they call, the term that is typically used is either advective or hydrodynamic effects. Some flow is taking place. And this flow may involve, either natural convection or forced convection or even diffusion. In the case of a plug flow reactor, for example, if you have a plug flow reactor, then if you take a look at any thin element, you have not only reaction taking place in that element, but you also have diffusion in and out of that thin shell. So what we are looking at is basically reaction kinetics plus its effect due to transport. This is the essence of what we are covering. Um, I mean, and let me now point out why it is different. Why it is different in biological reactors. So I should point out before I proceed. Um, I think I should point out that uh, it is my personal view that uh, have you done this stuff in chemical engineering? All of you have taken a similar course in chemical engineering.
Yes.
Yes, sir.
So I mean, I'm telling you my personal view. This is not maybe the view of the department, but my personal view is that there is an unfortunately large amount of repetition in the departmental courses. Right, there is really no reason to do it once in chemical engineering and once in this department. There will be concepts that will be repeated. They have already been done in chemical engineering, and they will be done again here. But hopefully, the chemical engineering course will disappear within the next couple of years. Disappear meaning DVV students will do it only in this department. So the way I'll be teaching you is that course, which is being designed for the coming 2 years, when we will teach as if you have not done anything in chemical engineering. So that's the direction in which we're going. No courses will be done in chemical engineering in 2 to 3 years from now. We're going to phase out of it and offer these courses within the department itself. Now, so that leads me to the question, since you have already done it, you probably asked the question, why am I doing it again? Well, actually, it turns out that there is an important difference, which I will now sort of highlight. It changes primarily the um, it changes not the general principles but the results. So the main difference is not so in CRE the reactions, all the reactions you did followed what is called mass action kinetics, which is just a fancy name. This term is basically used to say that if you have any, uh, let's say, reactant going to product, right? The reaction is reversible. And in what you have done so far in CRE, when S, so let me maybe, so the main point is that the reaction rate, the reaction rate increases when S increases, the reactant concentration, I should just write when reactant concentration increases, or I should maybe I should maybe put it, and reaction rate decreases when product concentration increases. So this is the principle. If you increase the reactant concentration, the reaction rate goes up. If you increase the product concentration, then the reaction rate goes down. This is the general rule governing the reactions that you have seen so far. Well, the moment you come into the reactions that we are dealing with, this rule is not obeyed. So, um, um, for example, we will soon see that um, if I can write, well, it'll be in more detail. So, but in the in the process of growth, is cellular growth, cellular or microbial growth, you typically have something like the reactant is some substrate, which could be like glucose or maybe galactose or anything like that, and that is giving you this X is used to denote biomass. And then it can even give you some products and so on and so forth. We'll flesh this out a little bit more. And let's say this takes place at a certain rate. Later on, we'll be using the notation mu to denote this reaction. Then you can see that actually the net rate at which the substrate is converted to biomass actually depends upon biomass, because actually it'll turn out that your dsdt, the rate at which the substrate is converted, is actually proportional to the amount of cells you have, because the more cells you have, the faster the rate at which you will consume the substrate. So now this is violating this particular rule that you have used in chemical engineering. In this case, what we find is that the product actually stimulates the reaction rate. It does not inhibit the reaction rate, it stimulates it. In fact, what we have here are commonly known as, and I think this is briefly touched upon in chemical reaction engineering, what we have in biological systems are what are called, at least in the processes that involve cellular growth, what you have are autocatalytic reaction kinetics. So they are not mass action. These are non-mass action. Yeah, because the product the product, and I should say which is biomass, is just one of the products. You can even have ethanol. You can even have butanol. A product is in this case biomass stimulates stimulates growth. So because of this fundamental difference, the results actually change, and in some sense, they become completely opposite. Uh, so I'll give you an example. I don't know. Did you in chemical reaction engineering? Did you cover, for example, um, which reactor is best for doing a reaction? Is it batch reactor or plug flow or CSTR? Was that covered in your
Y-
in your
Yes,
in your
sir.
course?
Yes, sir.
And what was the answer? What is the best reactor?
Well, it depended on the reaction kinetics, so order of the
Well,
reaction. It was
okay.
either
If it's first
CSTR.
order,
Yeah, I don't.
well, if it's first order, second order, what is it?
And it was a PFR.
Uh-huh. It was a PFR. Well, it'll turn out that it's just the opposite in this case. It'll turn out to be a CSTR. So, in that sense, uh, the picture changes, and well, you'll start to see the differences. Actually, um, uh, another technical term often used to describe these things is that the kinetics become essentially much more tricky when you have cells growing. You will see things that you never see in a chemical reactor. Like suddenly the reactor getting completely wiped out. It just nothing is left under certain conditions. It just completely disappears. Um, Let me now give you the evaluation policy. So I think I didn't teach last year. I was on sabbatical. I started teaching only this year, and last semester I had points for. There's an institute rule that you can't just have pure exams. There has to be something else. Well, I tried that, and it was a disaster. I mean, I had class participation. Nobody showed up, and the institute said you have to give them credit. So this time there will be no points for anything but exams. Okay, so it's three exams, one minor, two minors, and a major, but all three have the same weight, 33.33% each. The majors will not be cumulative. So each exam will cover only the previous uh, few months. Um, I think that that should basically cover it. I mean, I'm not gonna keep any attendance or homeworks, or I will give you problems to practice, but it has not worked out, right? It simply doesn't. Like two guys show up, you take the recording, and it didn't work out. So I think my policy is nothing but exams, period. And uh, I mean, I'll give you the general breakup of the syllabus right now. In a moment, I'll be doing lots of problems. So I might also just add, um, there is no penalty for not attending. I mean, I actually don't have an attendance policy in any of my courses. Yeah, but I do not pass people if they fail. That much you can please spread the word around. Okay, if you fail, you fail. So then don't. I just don't. You score less than 25, you get an F, and I don't care if you've been here for 6 years or 7 years or 8 years. Please don't come to me. All right, I just don't. Ask some of your seniors; they will tell you that they are. So that policy, I'm totally clear. No attendance, and uh, it is useful if you come. If you ask questions, I think you can get more understanding. Uh, this is the way I think it is, because my material is not taken straight off of the book. There are and there will be lots of numericals. So this will not be like your normal DBEV courses with the express the advantages and disadvantages of this reactor or that reactor, or tell me what a continuous reactor is. There will be no verbal questions at all. Zero. Only numerical problems and derivations, which is the way one expects people from IIT to function. Is that part clear? Any questions about that? So
Uh,
evaluation policy, equal weightage for all three. Okay, go
Sir,
ahead.
Yes, that's clear.
sir, there is now only one minor. So
Then
how,
then then it
how
will be 50-50.
okay, sir.
Yeah. I mean, it has not worked
No,
out.
sir.
I
I
have.
guess I guess most of the students would prefer more number of tests, like three tests, because
Yes,
I
yes.
guess you can schedule more
Yeah,
than
you
one
can
test.
schedule. Yes, that is what I
No,
wanted.
I mean, it's that is also. I mean, I just don't want to do any more than I have to, because I had it last time. I had all these other metrics, and it was a total waste of time. You understand? I mean, I had the class participation, I had presentations, but when two people show up and they only show up to tell you to record, I mean, the whole thing is a scam, right? I mean, so I said no more. It's I get down to the basics now. More exams, me, I think. Are you basically saying that it reduces the risk of poor performance?
Yes, sir. And you can, I mean, you can schedule two minors if you want to. I just wanted to tell you that now you only have one minor in your online semester.
I'll think about it. For now, I am strictly following the minimum guidelines as it stands, and lots of problems will be done in class, much more than in the book, right? I mean, you will have no excuse for saying that he didn't do enough. So, um, if you have sat through the lectures, it really shouldn't be a problem. But the exams will not be. You will not find a single question A repeated from the past. D having anything to do with silly descriptions about this or that. Explain this or explain that. None of that crap is going to come on the exam. It will be straight out numerical problems, straight out derivations of expressions. Okay, and I will see if I want to make it three because this is a class of 65. I mean, I have to see how I do it. Maybe if I can design uh, appropriate quizzes on Moodle, I'll let you know. But at this point in time, it is 50-50. Okay, because
Sure, sir.
I have to declare the class policy in the first lecture. If I modify it, I will explain it to you after discussing it with the head. But yesterday I emailed him and told him that I will not deviate from the bare minimum exam requirements because last time I had all these other metrics that were ultimately thrown out of the window. Because we were told that we couldn't use it. So that's where it stands right now. Okay. And now, I mean, let me see if I can. Um, so, um, just give you a overall picture of the course. Uh, let's see. So, the course will proceed as follows. The first topic will be stoichiometry and kinetics of reactions. And I don't know the extent to which you have covered it, but maybe you have. But here we will basically look at um, actually single, how to describe single and multiple reactions. And really, actually, it won't be simply like description, but actually, we'll start off with the single ones, explain why they work, where they don't work, and what forces us to go to multiple reactions. Once I'm done with that, then this is maybe I should, this is like the next three sections are actually applications of transport phenomena. So this is, if you will, crudely put, this is fluid mechanics in reaction engineering. So this will basically address the question: how do you decide that your reactor is? I mean, how do you decide? So basically, we'll come up with criteria. This is mostly about developing criteria for good mixing, and that means that the liquid is well mixed. Uh, the solids, uh, the cells, by solids, I mean the cells that are in the reactor also have to be well mixed. Why they have to be well mixed, we'll explain when we do the course. And also, you generally pass air to the reactor. You want that also to be, gas is also well dispersed, is well dispersed. So it's spread throughout the reactor. So this is the part that covers fluid mechanics. And ultimately the net goal of all this is to find out what is the power that is required to accomplish this goal. So this is power required to achieve the above, to achieve the above goal. And then the third part is again transport phenomena, that is heat transfer, and heat transfer in reaction engineering. This is actually, I might skip it because you've done this. This is really trivial. This is essentially all about calculating. So actually, it turns out, I should mention here, that heat is released when cells grow. And it turns out that there's a very simple thermodynamic, very simple, uh, very simple expression that can predict, that predicts uh, how much heat they release, how much heat they release. This is actually, it comes out of thermodynamics and basically says that the more oxygen they consume, the more heat they release. Okay, this is the main thing. This is basically how they release heat. And the second part of heat transfer. So this part is actually thermodynamics. It's not strictly speaking. This is thermodynamics. We'll cover it. The second part, you've already done it many times. It's basically if you know how much heat they're releasing, then what kind of a cooling setup do you want to maintain a constant temperature, right? So you basically what kind of a cooling system do you want to design to remove the heat? So this is the third topic is design of cooling systems. This I'll skip. This is you must have done this, right? Is it fair to assume that you've done this, these overall heat transfer coefficients, and that part is done?
Yes, sir.
Okay, all right, we'll skip that part. And then finally, this is an important, the last topic from transport is basically mass transfer. So this is four. Um, four is mass transfer in reaction engineering. And what is the most important thing in mass transfer turns out to be delivery of oxygen. Delivery of oxygen to the reactor. And, this is a very special, uh, not very, very particular part of what you've already done in mass transfer. So basically, in a reactor, you actually bubble air. There's a sparger here, and air bubbles come out. So these white dots here are the bubbles that you know you can make sure that they're dispersed. And the idea is to figure out what causes. So if I can blow it up, this is a bubble, right? These are all bubbles. I'm blowing them up in size, and then from the bubbles, it is actually from the bubbles the oxygen goes into the liquid, where the cells which are living in the liquid consume the oxygen. So if I may blow it up, this is a bubble, air bubble, sitting inside, floating around inside the reactor, and this is a cell, which are typically much smaller than the bubbles. Inside the bubble there is air, and oxygen comes out of this into the surrounding medium, and so you have oxygen dissolved in this liquid phase here. So this is actually right here in the open space. You have dissolved oxygen. That dissolved oxygen is then pulled in by the cells, and that's what keeps them going. And this entire portion is about what determines the speed with which oxygen comes out of the bubble and into the cell. I mean, is it available at a speed fast enough for the cells to survive, or will the cell's oxygen demand exceed the amount of oxygen that is being supplied from the bubble? And these are again just hydrodynamic factors. You have to make sure that you're agitating it well enough, or the bubble size is so small that there is enough surface area for the air, for the oxygen to get out of the bubble into the liquid, so on and so forth. So this is, I should just put it, it is more of what you may have covered in the name of gas liquid transfer. So this is interphase transfer of gas from the gas phase to the liquid phase. Is that does that have you covered this in some way? If not,
No, sir. We are doing the chemical department course on mass transfer this semester.
Okay, all right. Then once we are done with all this, then we start looking at different types of reactors. So just as you would have done in chemical engineering, uh, you can have batch, fed batch, or semi batch, or I think they call it semi continuous, continuous, so on and so forth. But we will do a lot more. The main focus here, so recycle. I remember one more. It's not coming to me. Anyway, so the main thrust here, the main focus, actually will be to find the relations between them. So actually, it turns out that if you know each of these reactors is actually capturing a small slice of what is happening in the continuous reactor. I mean, once you know what is happening in the continuous reactor, you can actually kind of predict what will happen in any of them. You're just capturing a slice. That part I want to make clear. So that reveals the relations between them as opposed to an orgy of reactors that you're just saying, ye bhi hai, wo bhi hai, aisa bhi hai, waisa bhi hai. They're all ways of capturing a certain slice. That's the main thing I want to go through. Now the last part is I don't know if I'll have the time, but it is on uh, data consistency. And this part uses what are called elemental balances, which I'll explain in a minute. Huh? To explain to this is to, to check data quality. So this is basically, when you run a reactor, there are certain things that have to happen. For example, carbon in must be equal to carbon out. If this is not happening, there is something wrong with your data. So this is basically uh, the theory of once you have the data, how do you check that what you have is sensible, right? So you want to know that everything is working out. Similarly, oxygen in must be equal to oxygen out. How do they find these things out? That is the last part. This I don't know to what extent we will cover. So, topic number 6, and I would say this topic. I don't know how much of it I will do. We'll find out when we go through the course. So, does that give you a broad overview of the course? Do you have any further questions? Any? Is there anybody still there, or have you turned your switches off?
Yes,
So
sir.
we are there.
Uh-huh. To what extent does this overlap with what you already know?
Sir, I guess the initial parts quite a bit would be like overlapping, but like obviously the difference would be the one you mentioned, that the difference between CRE and the cell growth reactors.
Um, I mean, to what extent has the interaction of transport phenomena with reaction engineering been covered in these courses? Can you hear me?
Yes, sir.
Yes, sir.
Uh,
So could you
what?
please reiterate the question once?
Yes, sir.
So I'm saying to what extent, almost, I think 3 out of the 6 topics. So certain topics I know have definitely not been covered, right? Like these elemental balances are not done in a typical CRE course. The last topic, this is topic number 6.
Yeah, so they haven't
Um,
been.
I'm curious to know to what extent the interaction of reaction engineering with transport phenomena, for example, fluid mechanics and reaction engineering, the topics that are covered they're actually empirical relations. So they're not exactly. So these are empirical relations that allow you to design how to make sure that your reactor operates in such a way that the gas is well dispersed, the solids, meaning the cells, and as well as the liquid in which they are suspended, are both well mixed. Has this been
So I
covered?
guess like what we did was more of a standalone CRE and standalone fluid mechanics and heat transfer. We didn't actually have a combination of all three per se last year or last semester.
Okay, so then I think that more or less, I certainly know that in heat transfer, the formulas that show the simple relationship between heat released and oxygen uptake, that's coming from thermodynamics, which I'm told you people don't even do in any detail. So we'll see how we go through that, because the thermodynamics course, which used to be one of the courses that DVB students took in Chemi, it was removed in the last curriculum. But this one topic sort of requires it. So we'll see how we do it. If nothing else, then we'll at least learn just the net result and proceed forward. So that's the essence of the course. And I think evaluation is also done. Is there anything else that I need to tell you? Um, I can actually send you a detailed syllabus if that's what you want. Uh,
Yes, that would be
uh,
nice.
Although I can actually really tell you right now, uh, topic number 1, which is stoichiometry and kinetics, that is actually more or less my own stuff. Um, I'm kind of making it up based on my own understanding. I did not find what is in the books to be terribly helpful. Chapter number 2, so topic number 2 on interaction of fluid mechanics with reaction engineering, and topic number 3 on interaction of heat transfer with reaction engineering, and topic number 4. These are all covered from Doran. If I remember correctly, chapter number 8, 9, and 10 uh, deal with uh, these things. Chapters 8, 9, and 10. So that corresponds to what I cover as main topics 2, 3, and 4 on interactions, on interaction of reaction engineering with fluid mechanics, heat transfer, and mass transfer. And then the fifth topic that I cover, which is the different types of reactors. This is again I do much more than what Doran does. Yeah, because I think her coverage is basically too elementary. That's purely based on my own reading of the literature. And the last topic, which is on elemental balances, that I cover from Willardson, chapter 3, and Ruels, which is the second reference, right? Chapter number 1 and 2. I think that should cover it. So I've actually given you all the books too that I use. Any other questions?
No, sir.
Okay. So
Uh,
here I will be covering a lot of problems. I will also be giving you a lot of problems to practice. Uh, I'm happy to answer questions privately, or maybe if there are lots of questions in the single sessions on solving problems. But we will be doing, so chapter 1 is kind of theoretical. There's not a lot of stuff to do by way of problems, although, but effective second part, fluid mechanics, the numericals, there'll be lots of numerical problems. Okay? So I think that should take care of everything that we needed to do in the lecture today, which is just to give you an overview. I will post the detailed syllabus in Moodle. By detailed syllabus meaning, as part of a certain program we are developing this course. This is the template that I've developed, and it's the template that I'll follow. So I'll post it on that thing either by today or tomorrow. And I also want to point out that there are also labs that are to be done with this course. I've chosen not to do the labs this semester, largely because I think that it's kind of silly to do these labs on the net. I think it's absolutely dumb. I mean, you might as well not do it and just pretend that you are watching somebody do some crap on a video. So the plan is to do the labs in December. And I hope that through the labs we will also introduce some elementary. So I'll see whether I do this in this course or in the lab course. The intent in the lab course is to basically explain to you the principles of the sensors that are typically used in these reactors. So these reactors are typically equipped with a lot of sensors. And it has been my unfortunate experience that most of the students, especially the graduate students here, they just note down the numbers without really knowing what the device is really giving. So the idea is to maybe use this lab course as a mechanism for introducing to you the underlying principles of the devices and using some statistics to really simple statistical ideas to really know whether the data you are getting is good or not. Not fancy, high end. This is really most of the physics, most of my statistics is taken from books written by physicists, which is like applied statistics, not this mathematical stuff that really I can find no use for it. And that I think requires a separate course. So I have decided not to do 332P along with this course. That will be done in December. So hang in there. I think you may, but many other things will be kind of repeated in December. So to give an example, in chapter 2, when we cover interaction of bioreactors with fluid mechanics, when we cover interaction of mass transfer with fluid mechanics, we use the main problem, as I told you, is transfer of oxygen from the bubbles to the liquid, and then from the liquid to the cells. And to find out the speed with which it is happening, sort of a measure of the speed, intrinsic speed. We use a certain thing called a dissolved oxygen probe. I'll mention it. I might even mention the general principle that is used by which it works. But it is the lab that will show you how the measurement is actually made. Okay, so unfortunately, the labs will not be in conjunction with the lectures this time, but that's fine. We'll cover it in December. So if that's good enough, then we can call it a day today. And the next lecture is on Thursday, 9:30 to
Yes, sir.
10:50.
Yes,
Is that
sir.
correct?
Yes, sir.
Go ahead.
Yes, sir.
Somebody-
The next lecture is on Thursday.
So we will proceed in this way. And as far as, like I said, if the numericals, lots of numericals will be assigned, and it's in your best interests to solve them. I don't think you'll learn a shit by sitting and regurgitating memorized crap. If you need additional lectures to explain the numericals, that I'll be happy to do. Okay? All right, so let's get started on Thursday. Fair enough?
Yes, sir.
Okay, all right. Thank you.
Thank you, sir.